So tonight we're going to have a conversation. It's going to be a moderated conversation for about 40 minutes where we're going to feel like a very privileged fly on the wall to a super interesting conversation. You're going to have your questions ready because then we're going to go to you. We're going to do like 20, 30 minutes of Q&A and have a feeling that there'll be a lot of questions. So a little bit about our moderator to begin with. So Curtis Morgan is our moderator. He's also a senior editor at the Miami Herald, where he oversees coverage of the environment, climate change, hurricanes, and growth. You know, all the positive fun stuff, right? He's also a Miami native where he's worked at the Herald for the last 38 years, writing about everything from bridge and building collapses to rare butterflies. An interesting fun fact is that he once swam with alligators for a story and vowed to never do that again. Ladies and gentlemen, it's a great pleasure to welcome Curtis Morgan.
Thank you, sir. Well, hi everybody. It's a pleasure to be here. I guess the reason I'm here is I was the editor on this story. We were the Herald was the first to mainstream publication to write about this subsidence study, and I'm guessing a lot of you are here because you read it. So we appreciate the support, and if you didn't, please subscribe. That's my little pitch. So I'm going to introduce Dr. Falk Amelung, and he is a professor of geophysics in the Department of Marine Geosciences at Rosenstiel on Key Biscayne. He received a doctorate in seismology from the University of Strasbourg in 1996. After a few years at Stanford University and the University of Hawaii, he joined the University of Miami in 2002. His research group primarily uses space geodetic data derived from the interferometric synthetic aperture radar, InSAR is the short word for it, to study active volcanoes, tectonics, and land subsidence, the latter of which is why we're here. So, here you go.
Okay. Okay, thank you very much, Curtis. It's a pleasure to be here. So normally I'm studying volcanoes most of my time, and so in this case there is really a great interest of the public. So it's great to see interest in the research what we are doing. So shall I just start?
You have a presentation that's going to sort of explain the background for those of you who didn't read the story.
Yes. Okay. Yes, so we are using satellites. This is a European satellite. It's the main satellite what we are using called Sentinel-1. And this lady is the postdoc who was working with me who did most of the work, Farzani. It started with this, was what of course all of you are aware of. The Champlain Tower South collapsed, and after that, everybody was thinking, at least in our community, So what can we do? I'm normally studying disasters anyway, natural disasters, and this clearly attracted me, and so we are using the satellite technique. The satellite technique can measure deformation at volcanoes, for earthquakes, try to understand tectonics. And so what we were wondering is, would we be able to see some precursory displacement at this collapse site? Would have been possible to forecast that something is going wrong. And then the other question is, could the geology play a role? Of course, we all know, well, we're on a barrier island. I'm going to come to that later. But we are on limestone, and limestone could have some particular properties. In limestone you get caves, so you can get holes can dissolve. This is an example of our data, a so-called interferogram. It's the combination of two satellite images which were taken a couple of days apart. The way how the technique works, so we're having our satellite. It's an active imaging instrument. That is important. It's not just taking photos. There's a radar on top on it, so it sends a signal down, and then this signal may go back. The signal goes back to the satellite, and then when we have some displacements, like here, very tiny displacements, we can measure it. We can measure it, and the reason why we can measure it is that the wavelength of the satellite is the radar is pretty small. 5 centimeters or so. We are doing something which is called interferometry. Then we can measure very tiny displacements. Okay, so we are having our displacements, and then the satellite flies over it again, and so we can track the deformation. So an example of what gives us the measurements. If we are on the ground somewhere, for example, there's a boardwalk or something like that, so the satellite images, it goes to the ground, it gets reflected somewhere, it goes back to the satellite. In the case of the Porsche Design Tower, for example, there's all these kind of things here on the top. We get measurements on the rooftop if there is something which is oriented in the right direction, so that the radar signal gets, or the radar wave gets scattered back to the satellite. If it's a little bit off, then it doesn't work. But this is what we call corner reflector. So on the top of this building, on the rooftop, there's lots of potential corner reflectors or persistent scatterers. We call it persistent scatterers, and then the balconies, for example, the signal can get reflected, and then it goes back to the satellite as well. And so the whole technique is computationally expensive. We are using supercomputers. We are working in Texas. That's funded by the National Science Foundation. And now, before I come to the observation in Miami, let me give you a little bit of background about the geology of Miami. Florida. Of course, we are on the Florida platform. There is not much topography, as we know, in particular in the south. So the Florida grows and shrinks very rapidly on geologic terms with sea level. 20,000 years ago, that was the last glacial maximum. We had a big glacier in North America and Canada. That was the size of Florida, much bigger than it is now. In 200 years, it's going to be smaller again. Sea level is going to be 6 meters higher or something like that. So then, the black area is going to be the size of Florida. That's going to be in 200 years, and it happened the last time 120,000 years ago. And 120,000 years ago is when the geology, what we have, the Miami limestone, when it was deposited, when the sea level, when all this was under the water. And that happened many times before in the history, in the Pleistocene, the last 2 million years. Rivers were meandering, Florida was growing and shrinking. And and then the rocks which were deposited is something like this one, the Miami Oolite, that is in downtown somewhere under the metro rail. This is a pretty strong rock, but then we also have limestone which looks like this, which has lots of holes. And this is a typical rock on the Atlantic coastal ridge, the dark red area here. But we are, of course, in Miami Beach, we are on the barrier island. The barrier island, this is how barrier islands looks, which are not developed. This is in Virginia somewhere. They are created by sand quartz sand transported from the Appalachians by coastal currents. They come down here south, and the barrier islands, they move all the time. When sea level goes down, they move to that side. When sea level goes up, they move to that side. Okay, so now to the results of our study. We looked at a 7-year time period. We had a total of 220 or so images, and most of this, what we see here in this, is green. Green means no displacement. But then there's quite a lot of blue dots, and this blue dots is subsidence at a rate averaged something like up to half a centimeters per year, which is not very much, half a centimeters. But of course, over a long time, it's going to be significant. So I'm going to go through that in some detail. So we saw the subsidence happening in particular at the high rises, essentially almost at the high rises. And so that is some of these 35 buildings. This is northern Sunny Isles Beach. We have something similar in central Sunny Isles Beach, so particularly in Sunny Isles Beach, Bal Harbour and Surfside. And then if we come down here to where we are, to Miami Beach. So in Miami Beach, there's actually pretty little. It's all green. There's a couple of blue dots. One of them is L'Atelier, and then right here the Faena House or hotel. I'm not sure whether it is. But see how much it is.
Are we safe in here right now? We're safe, right? We're safe.
For now, we are safe.
Okay.
Yeah.
Thanks. Okay, keep going.
If you come back in 100,000 years, it will have gone down.
All right, well, that'll be the next question when you're done. Go ahead. Sorry.
So this is 1 centimeter or something like that per a total over 7 years. So it's really not very much.
Okay.
We have the Faena Forum also next to it. That is a newly built structure. We don't get any data, and the reason for that is there is not really any balcony, so there is no scatterers. But so to summarize, in Sunny Isles, almost 70%, Sunny Isles Beach, 70% of the structures are subsiding. Significant also in Surfside, in Bal Harbour and Miami Beach, just very few. And let me give you a summary of how accurate that is, or how we are doing this. So this is Oceana Residence, somewhere in Bal Harbour. We are seeing blue dots over here, which are off the building. And the reason for that is the satellite looks from there. When it comes to a scatterer, it can come back either from there or it can come back from the ground. That is obviously important to know. Do we have measurements from the building or from somewhere else? And then what we can do with this technique is we are measuring the elevation. The elevation, red, means something like 80 meters. And that really agrees with the height of the Oceana residences. And then we can use this information to correct the location. Okay, we know these pixels are 80 meters high. Okay, then actually they will fall right on the building. But so that's surprising results. We have a few blue dots which show significant subsidence. Well, significant, something like 5 centimeters or so, and then we have the green dots which show nothing. So how can that happen? Could that be differential subsidence right under the building, or could that be, that would not be good?
What's differential? Can you explain that to
yes.
them? Yeah.
Okay, differential subsidence or differential settlement. Okay, so when a building subsides, when the whole building goes down, it doesn't really matter very much because the whole building goes down. And when these high rises are constructed, they are taken into account. And the big ones, okay, the developers don't talk about it, but they can go up to 30 centimeters. That has been observed. But it's taken in account into a design. If you get differential subsidence, a little bit more, then that can cause problems. Not if it is 1 or 2 centimeters, but if it goes to 10 centimeters, that can cause problems. It's not going to collapse, but you can start getting cracks. So here we were worried, okay, why do we have dark blue dots and green dots? And then we look at the elevation, and it turns out one of the light green dots, they have essentially 0 elevation. So what is happening there is, okay, we have the opening where the satellite is imaging from the west actually, and then we are having scatterers on the top. We are having some scatterers here in the opening, and it gets reflected back and forth. So that gave us quite some confidence that these measurements are real. Okay, what causes the subsidence? So we were able to get a few geotech report. A geotech report is something what the developer has to do before to design the foundation. They're drilling in there, they're doing experiments. We were not able to get very much, unfortunately, but we got a few, and the yellow is sand, the gray is limestone. What we see is that in the north, where the Porsche design tower is, we have quite a lot of sand, and then if we go further to the south, we have less sand. But on the other hand, we have very little information. We have for this 87 Park Tower, we have up to 40 meters or 35 meters. That's how deep the piles go of the foundation. And in Miami Beach, we have only this one information. So there's quite a lot of sand in there, and some views of the United States Geological Survey, they have some drill holes, and they make their data openly available. We can go to their website and look at it, and so it's somehow quite interesting how the geology looks. Here we have 25 meter depth, the typical limestone, but then actually we're having voids somewhere. These voids, that probably was a sandy layer, and it was washed away. Here, this is 60 meters depth. Somewhere else, there is quite a lot of sand. This is sand brought from the quartz sand, probably brought from the Appalachians. So we have sand layers. There's a couple of places, not from the places where we studied, somewhere else in Miami Beach. We have core information, so you can see how this limestone looks like. This limestone has some holes in there. Not everything. Here it is more solid. There's quite a lot missing, and why it is missing? Because there was sand in between. Okay, so I'm going to go over this very quick. So what causes it? And so these kind of studies are done all around the world. Groundwater extraction is a typical explanation. We don't do it here at the coast. Then we have consolidation. That is what people are worried about if you build a high-rise in Chicago, for example, in the alluvial, in the recent sediments. You can get that. We don't have that. We don't have that here. Okay, I should go forward. The natural compaction under the weight of the structures, probably not. So one possibility is that the subsidence is construction related. So what we think, what is happening, okay, you're building a high-rise, there's a limestone, the gray, the yellow, the sand in between, and the sand is loosely packed. But then somebody is building a new building nearby, and there's quite some vibrations, and when this vibration is happening, first it goes in this side, so essentially seismic waves, then it goes back. What you're ending up with is you're changing the packing of the sand, so you're ending up with something more dense, and the result of this is, of course, that there is subsidence at the surface. In particular, if you have a heavy building on top of it. So there's one explanation. Another explanation, so about that we are pretty sure. Of course, we can't be 100% sure because we haven't really drilled in there. We need sand samples to test it. Another explanation is that for the construction there's lots of pumping going on, and then when the pumping is happening, water is flowing. That can have a similar effect. So the sand grains may be rearranged as a result of that. And just as an example of how this works, this is my tea. So the sea is changing its packing and it loses quite a lot of volume. So let's look at a couple of those buildings in detail. The Ritz-Carlton residence. Okay, what we see here is sort of what we call an exponential decay. That is okay. If that's it, that's good because it's going to end eventually. So that could be an after effect of its own construction. It was built in something like 2019. So we get data only once the structure is finished. Before that, during constructions, we don't have because there's nothing permanent on there. But then we have another building here. Okay, this is a signal. Not much was happening, and this happens to be right next to the Ritz-Carlton. While the Ritz-Carlton is built, we see 2 centimeters of displacement relatively fast, and then it goes again slower. So okay, what could be, but we are not sure. It's a hypothesis. It's related to the construction of the high-rise next to it. We have the surf club buildings in Surfside. They show an interesting signal. So here nothing happened, then somehow it goes down. So each of those dots corresponds to 1 satellite image taken. So we have 220. It goes down suddenly, and yeah, the same even over here. One of those pixels is not indicated here. One of those points is located on this building, pretty far distance. So what could be the cause? Well, we don't know, but what we know is there was a construction here, the Arte residence. Maybe it's related to that. And so that's why we say it's construction. Well, construction is pretty likely one of the reasons. And then we have some other signals. For example, some buildings show more or less a linear subsidence. For example, in particular, the Regalia high-rise, which was built in 2014. So why do we get, it's not much, it's only 2 centimeters or 1.5. So why do we get linear, steady subsidence or settlement? And so we don't know, we can just speculate, but the possible explanation is it's grain rearrangement by tidal flows. The tides twice a day going there through the sand, and maybe if you have a heavy load on top of it, that's going to cause it. And then another potential explanation is dissolution of the limestone. And so on the barrier island, we are having fresh water right under us, but only for a couple of meters. At greater depth, we have saline groundwater. The limestone or whatever is at depth is saturated with salt water. And so what is happening now is if you pump water in there, or if you put fresh water in the limestone dissolves. That's why we have in some places caves in limestone. Limestone, putting fresh water into limestone is not a good thing.
Well, we also inject all our flood water in deep well injections up and down the barrier islands here.
Yes.
Correct? Is
yes.
that a contributing factor?
Yes. This is an image.
There you go. Okay.
Of all the wells what we have. That is something what came out during this study, or actually, partly thanks to people who were being concerned. So that's an example of a well. This is not very, you see this probably somewhere here in Miami Beach. It goes up to 30 meters, and then somehow the fresh water goes in there. In some places, they put it under pressure. You have the limestone with the holes. If there is limestone with the holes, then you put the fresh water in there, you can get slow dissolution. And our hypothesis is, okay, if you have heavy building on top of it, then this may go even a little bit, this may go faster, it will go collapse. But it's speculation trying to find the reasons for that. So as a summary, as a first summary, we see the subsidence not only at new structures, also at old structures. These are the structures which were built before 2010. this is the amount of average velocity, something like half a centimeter to 2 centimeter or so. It doesn't make too much a difference. So we do see it at old buildings. So what about the Surfside, the Champlain Tower South? We do have data for that. Some persistent scatterers on top of the roof. We don't see any signal. And that was really surprising, because we know the 87 tower, just south of it, there was heavy construction going on while it was built. So we really would have expected to see some subsidence related to that, but we don't see it. While the 87th tower itself, it has some blue dots. It is subsiding, not very fast, but it does. So. But with the satellite technique, we can't really observe everything. We can observe the rooftop. In the case of Champlain Tower South, we know there were cracks on the pool deck, and we're looking from the other side. So we don't have any data for the relevant part. Okay, where else do we have subsidence or settlement? Actually, quite a lot. We haven't studied it in detail. In downtown Miami, there's significant, lots of blue dots. The problem is here it is really difficult to find out when you have a settle from which building, because there's so many high-rises, from which building, the blue dot to which building it represents. So should we be worried? These high-rises are built very strong. Example of a foundation here. Even if you get 1 or 2 centimeters of differential settlement, differential movement, it doesn't really matter. Last summer I was in China. Well, I look now before I go somewhere to a high-rise. I do process the data to be sure. There's lots of high-rises.
So there is something to be worried about there.
Well,
okay.
I convinced myself. Yes.
Okay.
So lots of blue dots. Rates are significantly higher, up to a total of 20 or 30 centimeters. There were even some cracks, and the buildings are. I'm still alive. The buildings are still standing.
Okay.
So it didn't really matter. But it shouldn't be ignored. So differential subsidence is what matters regarding not whether it collapses, but whether a building can be affected. And so here, for example, we haven't looked at it in detail, not systematically, but here for the 87 Park Tower. Here, if you look at this, these dots are having some slightly different color. So there's a difference in 0.3 centimeters per year, or over 7 years, it's 3 centimeters or 2 centimeters differential subsidence. So not very much, but and we are sure that these are on the roof, so they have the same elevation. But if it goes over 50 years, then yes, so there might be cracks. So it's good to know that and to look for it, and maybe you can fix it. Another thing is, what is about tilt? So in the study, we said there was maximum of 8 centimeters of displacement, but actually we do have a little bit more with another satellite. So for the Porsche Design Tower, it's a total of 11 centimeters what we see, which is not very much either. So we looked with a different satellite from the other direction. We are looking from both directions. We are looking from the west. We are looking from the east. So and this shows the elevation of the pixels. So these are just to show that it works well. So we see 11 centimeter from one side, 5 centimeter from the other side. So it looks to me that something like 5-6 centimeters or so it tilted over this time period towards downtown or towards Miami.
Okay.
It correlates with the winds. There's always easterly winds. So that is something to look at it in more detail. But on the other hand,
is this reassuring? This photo here?
It's tilting since more than 1,000 years.
Okay.
900 years. In San Francisco, there's a Millennium Tower. It was detected that it's tilted, not this 5 or 6 centimeters. but 70 centimeters. It stands, and people can repair it. It's costly, but you can repair it. But this tilt is research in progress, so we haven't really studied it in more detail. Okay, to summarize, okay, in the study up to 8 centimeters we saw, and we did see it at old buildings, older than 2010. It's caused probably by grain readjustment in the sandy layers. So if you have sandy layers under your building, you might get it. And construction vibrations, they are certainly contributing to it. Other factors, which is this hypothesis, is pumping for construction, tidal flow, and stormwater injection. The barrier island geology doesn't have any impact. So I forgot to mention it, but so the barrier island was caused the uppermost 6 meters or so of sand what we have here. The foundations, they go much deeper. So it really doesn't matter. Is there a climate connection? Not very much. There could be a climate conjunction if the stormwater injection really plays a role. We haven't investigated that. So stormwater injection and the dissolution of the limestone, we're going to get more rain when climate get warmer. But it's not a primary factor at all. Okay, so there was quite some coverage. So yeah, one example, Miami Beach under the water. So that's going to take, with the rates what we saw, 20,000 years. So don't worry about it too much. And so I'm going to close with this one. This is now a high resolution image. We haven't really used it. We used freely available low resolution image. If you do this Sunny Isles Beach, essentially for all these pixels, we would be able to get measurements if we continue doing this work. Okay, thank you very much.
Okay. Well, because of time constraints, I'm going to have people ask. But I do have one question, because you kind of talked about nothing is happening now. I mean, is there a timeline for when we need to be concerned at these? I don't know. Are you concerned about the rate or the extensive amount of subsidence?
So I think
how long of, but they're talking about sinking property values. I think that's the major concern in this room. Is there a reason to worry about these buildings anytime soon?
So if you have the whole building going down, if there's no differential subsidence, then there is not going to be much effect, except you're going to be underwater a little bit faster. It's not only sea level rise, it's also going down. So in the rates, what we have is something like twice as much. But that doesn't really, over the 50-year time scale, and over the 50-year time scale, if there is differential subsidence, then that can cause problems. If you start getting cracks or something like that, then you better fix it as soon as possible. Observe it, whether there are cracks, and if there is, fix it so that
so the good news is you might be covered with seawater before your building sinks into the earth, I think is according to the sea rise projections. But
so the subsidence, what we see up to now is same rate at sea level, at sea level rise. So if a building was constructed, a new one, expecting be ready in still be there in 2200, okay, maybe that's going to shorten the time. The flooding is going to come earlier.
Should we be altering the way we are constructing buildings? Should they be as big? Should we be doing, I think it's Surfside is already talking about some sort of different construction standards for vibrations. That was an issue after Surfside, after Champlain Towers collapsed. The adjacent building was sued for possibly contributing to the collapse. The Herald's investigation and federal investigators have never linked subsidence to the collapse of that building. And there was a settlement on the nearby construction stuff, but should we be doing things different? Setting tougher standards for vibrations and things like that?
Tougher standards for vibrations, for sure.
For sure.
And it's important to get the information. So when a high-rise is constructed, they are drilling in there, and this is very valuable information to understand what this building is going to do. If there is sand, lots of sand, okay, maybe this building is going to be a little bit less valuable than those where there is no sand. So it's important to know it. So for this building here, we didn't get the information. If is there only limestone, then it's not going to continue subsiding. If there is significant sand layer, then it's possible.
Is it vary from like site to site, or is it just you have Sunny Isles as kind of a hotspot in your research?
Yeah. So
Miami Beach, except for this building, no. Miami Beach has not a whole lot. So is there a great deal of variation?
Yeah, so why Miami Beach itself doesn't have very much? So there's two possible explanations for it. One is that there is not much sand at depth. The other one is there was not so much construction in the last 10 years. We don't know what it is. Whether there is sand or not at depth, the information is available. The city has it. Well, they don't have it properly organized, but this tests were done. You have to do it, and they do it very well. The geotechnical engineer, they drill up to 50 meters or something like that. So the information, what is there at depth, is there. If we have it, then we could make some more. Assuming our interpretation is correct, then we could make some more prediction of what is going to happen.
So you're talking about the core samples before you build to decide how.
Yes.
Okay.
Yes.
Is there any place where that kind of information is made available to the research community?
No.
Okay.
That is something. If something like that comes out of this, that would be very valuable. I think. Well, developers are not interested in it because they still have to sell their property. I understand that, but then once people are owning it, I think it is in the interest of everybody to really know what is at depth. And I think homeowners association, they can decide to put this information, make this information available.
Yeah, I was going to ask that.
And actually, it is public information. It is in the building departments. It's
right.
not.
But they don't retain it necessarily, do they?
They do have it. They have to have it. But it's difficult to find, and so we didn't get very much. So if the building departments, they just have to file the data what they get properly to make it easily available, which is not very difficult anymore. Just a PDF, putting it online somewhere, and then people can download it.
And if I own a place, in one of these beautiful condominiums, I read your story, I read your study. What do I do? Do I do anything? Is there something a homeowners association? The reporter who wrote this, Denise Harubi, is working on a story about some sensors, almost like seismic sensors that somebody's going to, I think one building has already installed them to detect if anything is going on that's worrisome. Is that a step that people should be taking?
It's possible, yes. And then you, if some construction is nearby, you can measure how much vibration, there is. I think as an individual or as a homeowner association, that's useful. It costs money, probably not very much.
Okay. Well, if you can afford one of these,
but I think the main in the long run, if you really know what is at depth, if you have sand, lots of sand at depth, then try to find an engineer. Okay, can we do something? What is the solution? We haven't talked about solutions at all, and that's not my field. But you might be able to grout it. Engineers are about finding solutions. And
you mean pumping underground to strengthen the
pumping? Yeah, something like concrete. But what is more fluid? What flows easier? But that could be a solution. But we don't really know exactly we're just speculating about the reasons, so we don't really know.
All right, well, for time reasons, I think we're supposed to open it up to.
I just want to start with a question. When I read this report in the Miami Herald, the first thing I thought about was context, right? Like, how do we put this into context? And I think one of the most famous buildings that you referenced was that building in San Francisco, the Millennium Tower, I believe, right? Which 60 Minutes famously did a whole profile on. That building you said was 70 centimeters or
yes,
tilting, right? So is that what you would call the worst case scenario of any building that you've seen? And if so, is there anything that remotely resembles that here in Miami Beach that would be on that scale of that concern? Because even that building at 70 centimeters tilting is of concern, but not where people are being forced out of their residences in order out of public safety and so on. Is that correct?
Yes, that's correct. So we haven't investigated. That is something what we hope we're going to get a chance to do, to really look in detail at the tilt, but hasn't been done. I just showed this one example, but we have no indications that it's of that order. So tilt, well, we know it. We see it from the Leaning Tower of Pisa. It's not really a big. It's not a big problem. Buildings don't collapse because of tilt. Differential settlement, that can cause problems, yeah. But they're not going to collapse. If you get cracks, you can fix the cracks. Make sure there is no salt water or from the air, any salt water going in. So I think it is good to know. If you really know whether there's any settlement at your building, then okay, think about how to solve it, how to solve the problem. Better to do it now than in 20 years realizing, oh, we had a crack and it got corroded.
Anybody else? We can't see you.
Can you talk a little bit about the Miami Rock Ridge, the area ranging from
The Atlantic Coastal Ridge, yeah. Okay, I will go back.
Here we go.
It was right at the beginning.
Can you talk a little bit about the Miami Rock Ridge and that area ranging from Coconut Grove, Coral Gables, Pinecrest, and so on, and if the Rock Ridge is susceptible to these issues as well?
I don't think it is. We don't really know what is at depth. So okay, the Atlantic coastal ridge over here, the highest elevation. It's having this type of rocks largely. Well, Coconut Grove, we looked roughly in Coconut Grove. We also do see a little bit of subsidence, but not very, or settlement, but not very much. So the fact that it's a coastal ridge, that is recent geology at greater depth, what is relevant for the for where they put the piles or where they end the piles, the fact that it's the coastal ridge doesn't matter. Same as that it's the barrier island doesn't really matter. So about the geology, you should think, so over almost 2 million years or so, big area, Florida platform, rivers going here, rivers going meandering, sea level rising, barrier islands moving back and forth. That's what happened. So it's a very messy geology actually, because of the fact that it was a platform.
Okay. Anybody else?
Yeah, good evening. Thank you for your presentation. One question that I have, when I read the article, I went to look at a couple of buildings and I paid attention to the threshold, and you mentioning that you had a differential of 1 to 5 centimeters. I personally, and I have a good eye to that, I couldn't see anything. So have you, when you, for example, you talk about the Porsche Tower, and you're mentioning the 5 centimeters, 7 centimeter actually, have you gone to see if you could see a difference on the threshold from the building to, for example, the adjacent structure?
Going there to see, you mean to the structure itself?
You mean like ground truthing, surveying it? Is that what you mean? Okay.
I mean, 1 centimeter,
Yes, so
5 centimeter is a lot. I mean, for example, you would trip on 2 centimeters. So I was wondering if you...
Well, one centimeter is not very.
Well, 2 centimeters you trip.
Yes. So if the whole building goes down, there is not going to be any. It's hard.
I agree with you. The whole building goes down. But for example, if the parking structure next to it was usually, when you build a building like this, I mean, Porsche Tower is different. But on some other buildings, the parking structure is built, separately. You would have what I call a threshold, means the entire structure of the building will sink, but do you see, like, for example, to the sidewalk, or do you see to the adjacent structure? Do you see a difference?
Yeah, so I didn't see anything. What people are doing, especially here at the coast, if there is some cracks or something which looks not good, then they're probably going to fix it. And so it's hard to know.
Yeah, I'm thinking, maybe I'm interpreting the question differently. We've got a lot, I told you, we got some pushback when we ran this story from the building community. This is just natural settlement. Builders and developers call this settlement, newspaper people call it sinking. He called it subsidence. And they were just saying, they were saying that this is not, there's nothing in here that is unexpected. Is that what your question is? That you're wondering if this was just something that would be in the normal course of construction, that this would have been anticipated? Is that the question?
No, I believe that this is a natural course. I do believe that it's a natural course of a construction that your building, will settle.
It will
but
settle, yeah.
The article was kind of like a bomb thrown into the community, and that's why everybody is here listening to it.
And Surfside, yeah.
And in Surfside, and now in Sunny Isle. And my question is like, yes, you're relying on information from the satellites, but you measure it, 1 to 7 centimeters, have you actually physically looked at it? Because you would see it. If there is a building sinking, you would see on the threshold a differential. It's obvious.
Yeah, so that is something when we started this, we actually hope to do it, to measure. So for example, you can put reflectors on a building and then also measure from the ground. But it's very difficult. You're not owning the building. You have to get the homeowner association involved, and there are so many questions asked. But so yes, it was suggested. You suggested that if people put ground-based measurements in there, or you can do it. If homeowner decides to share that, and then we really will have the data to compare the satellite data with the ground-based measurements. But we didn't go to the field to we looked for it, and it was very clear we can't see anything.
Yeah, and I think one of the things about this story is, if not for Surfside, I think this study would appear, and maybe some smart reporter would find it, and it would run in the inside of the paper, but there's just heightened scrutiny, heightened awareness, heightened concern because of that building collapse, even though it was not directly tied to this. So when we were writing the story, we were very cognizant, tried very hard not to be alarmist, because I don't think there's anything in these findings that is immediately alarming. I think researchers like to say, we need more research. Is that the case?
Yes, absolutely. So what we need to do, the main thing, one important thing is what we need to do is we need to drill, get a sediment core, hopefully from one of those buildings where there's significant subsidence, and then look, is there really sand? And how does the sand behave if you put it on a shake table and shake, for example? Does it really compact? That would be very useful. Just comparing the coastal structures with something high rises a little bit further inland will also be useful. But in all cases, we do need the geotechnical information, and we don't have it. The city has it. If the city would really develop a database, the city is having all kind of geographical information online. If they were having for the high rises, this geotechnical reports online, or this information how many sand layers there are, that would be very valuable. So if you had that, then we could really make big progress.
Yeah, and I would think that if some of these communities do take another look at how adjacent buildings are constructed, and take a look at things like vibrations, which cause other damage as well. I think if I lived there, I would be happy to see kind of tighter regulation on what was going on next door to my building. Anyway, that was just a thought.
That is also something what in principle.
1 minute?
One or two more questions.
One or more, okay.
And then we can take.
And then, sir?
Oh, here, sorry.
Oh, sorry. Yeah, you guys, I can't see anything, so.
If you yourself were purchasing a condo unit, something in the South Beach, Miami Beach area, what are the 3 things that you're looking for to feel that you have knowledge about the substance of what the building is built on?
So I would get the geotechnical reports. I would process the data again, be very careful. But it wouldn't really distract me if I see some subsidence. So the geotechnical report, is there lots of sand or not? If there is, then okay, I would ask, what is the homeowner association? How do they plan to deal with it? Do they have any plans to deal with it?
Okay, and then the second question.
I would look at the maintenance records and see how things are, because that's the gigantic and immediate concern and expense for many of these places.
And does it concern you when there's big potential structures being planned to build next to your buildings or not? Or does it not matter? It really depends on what they're being built on.
It would concern me. I would make sure that I acquire all possible data why this is going to be constructed. Yeah. For example, vibrations to know that, and you can put measurements. Well, the last thing what I want to do is to advertise for this company who is doing it. I just heard that they are that they are doing it, but you can put instruments in your building, as was said earlier, to see whether there's any much more precise than what we can see with a satellite, whether there's any displacements.
One last question.
Hello. Hi, thank you. So you mentioned that the reason of the subsidence is not due to the compacting of the soil, right? Which would, like the long-term settlement of the soil itself, of the different layers, that would be a linear settlement. And this study is considering a linear, right? Like
No.
a linear displacement for this building. So it's, my question is, are you projecting the current behavior to the future when you say that in 20,000 years, we will have 20
If it
centimeters
continues like that.
Exactly.
Yes.
So
Of
you're
course, that was a joke,
assuming
yeah.
that it continues to behave the same way.
If it continues to behave in the same way, yes.
Right. But it doesn't
so-
look like the reason of this behavior is a linear reason. I don't know if I'm explaining myself correctly, like clearly, but when you have your soil compacting, right, like the different layers, you kind of design for it, right? Because the geotechnical studies are made for that, so you kind of design for that. In this case, it sounds like it's not due to that; it's due to construction
Well,
or additional reasons. So I don't understand why the study is kind of projecting into the future a behavior that is not.
So the design, and I haven't got a chance to talk to any geotech engineer who's working for one of those companies, but to what I saw 4 geotech reports which we somehow got. They say settlement finishes a couple of months after the building is constructed, and our data show clearly this is not the case. But so the reasons, what we think is okay. So the construction vibrations is one thing, but then you have the other reasons. So construction vibrations, it's difficult to explain the linear settlement, and that's why we invoke the other.
Like a one-off across like 4 years, 2 years settlement, right? And then why would it go linear? That's what I don't understand. But I agreed with you when you talked.
Yeah. So why would it go linear? That's what we don't understand either. So that's why we think it is something which is more persistent, like the tidal flow or the stormwater dissolution.
I'm not the scientist, but yeah, if you've got these, this is the way we dispose of the rainfall. That we drill holes and we put it down into the rock, and that fresh water can dissolve that limestone over time, and that could contribute.
Yes, but so limestone dissolution rates, if you ask a geochemist, it's very small. Actually, it's easy to calculate it. there's so and so much water coming down, and it can take up so and so much cations or anions from or carbonate atoms. I'm not a geochemist. So you can calculate it. And the amount of subsidence, what you would get, or settlement, is very little based on that. But so if you have something like that, and then it gives way because there's a weight on top of it, that is potential explanation. But we don't know. It's speculation. Would be nice to figure it out.
With that said, I'm sorry, everyone, but we have a hard stop. I want to thank Professor, I want to thank Curtis, and I want to thank all of you. I think in summary, your investments are safe. Now, if you pass it down to your kids, you might want to give them a little bit of advice to watch that a little closer. But with that said, thank you, gentlemen. Thank you all for joining us tonight. Have a great week.